Hello. Today we're going to talk about nucleophilic acyl substitution reactions. So in this case, in a nucleophilic acyl substitution, you have a carbonyl group and you have a nucleophile, and that nucleophile now gives you a new or a different carbonyl. In this case, you have a OMe, or a methoxide, that ends up being a leaving group, or it leaves the molecule. So let's look at how this works. I guess before that, does this happen with any or every nucleophile? No. And we'll talk about different nucleophiles where this can occur. So, first off, we can think about the various bonds that are involved in this acyl group. And just to simplify the bonds, there are more bonds involved. We can look at, again, at this carbonyl pi bond and this the carbonyl pi star. So the pi star bond, the antibonding orbital, is the lowest unoccupied molecular orbital. So that is where the nucleophile with its electrons are going to target. Another way you can think about this is to look at a resonance structure of an ester. So again, this is the ester functional group. We can look at the ester functional group a couple videos ago to think about their reactivity. We could draw this resonance structure where we push the electron density from this pi bond onto the oxygen atom. You end up with a carbocation and oxygen with a negative charge. And you can see that the carbocation, the carbon with a positive charge, is where the nucleophile would approach. And that just so happens to be exactly where the pi star, or antibonding orbital, exists on this molecule. So let's look at the mechanism of how this occurs. So you have an ester with your nucleophile. Let's go ahead and give ourselves a more specific nucleophile. In this case, we'll say ethoxide. So it's deprotonated ethanol. To remind you of what that means, the ET is ethyl, and so there are all these implied hydrogen atoms as well. So ethoxide is simply a faster way of drawing that than drawing out all of these atoms. So we'll just stick with ethoxide for now. So the ethoxide, as the nucleophile, is going to interact with the electrophilic carbon of the carbonyl. That's going to push the electron density of this carbonyl up onto the oxygen, just like it did in the Grignard reaction a few lessons ago. And these electrons go up and wind up on the oxygen atom to give you this anionic species. One thing to note, again, is that if you did not push these electrons onto the oxygen atom, you'd have a scenario where you have simply too many bonds to the carbon. You'd have 10 electrons on that carbon atom, and that's not acceptable. Okay, another way of thinking about this mechanism is you could draw the resonance structure first, and if ever you're stuck, drawing a resonance structure is a really good way of getting unstuck. So in this case, this resonance structure tells us there's a positive charge on this carbon, negative charge on the oxygen. Well, your nucleophile has a negative charge. Negative charges are attracted to positive charges, and so you simply connect the arrows. That would also bring you to this same intermediate. This is a key tetrahedral intermediate that is involved in a lot of our mechanisms we're going to see. So being able to draw this tetrahedral intermediate is a really important step. So once you're at the tetrahedral intermediate, this is a high energy intermediate, and these electrons can come back down to reform the carbonyl, reform the carbonyl, and in that process, it can kick off what was on that acyl group. That's why it's called an acyl substitution. You are substituting one group, the ethoxide, for another, the methoxide. Or we substitute the methoxide away for the ethoxide. So now one thing to think about is, wait, this methoxide looks a lot like ethoxide. So could methoxide be a nucleophile? And the answer is absolutely. This is a reversible reaction in this case. If you simply had a 1-to-1 mixture of this ester and this ethoxide, you would end up with you'd likely wind up with a 1-to-1 mixture of the different esters. This particular nucleophilic acyl substitution reaction is called a trans-esterification. You are transferring one ester for another ester. So depending on when you're trying to decide what side wins, You can look to the stability of the different nucleophiles and potential leaving groups. They don't always have to be the same, and we'll see that in another lesson. And you can also look at reaction conditions. So, for example, if you wanted to get all of the ethyl ester, you could do this reaction in ethanol, so that way any molecule in solution that is likely to be a nucleophile would much more likely to be ethoxide than methoxide, and so you're going to drive your reaction to the ethyl ester using the Le Chatelier principle. And I'm happy to answer more questions about that in class or in office hour, and I look forward to your questions. Thanks.